One last comment and one last example from section 2.5. So the comment is that so far we talked about how there are 4 different possible indeterminate forms to think about right now. 0 over 0, infinity or infinity, infinity times 0, and infinity minus infinity. And we've seen several examples of 0 over 0. We've seen an example of infinity over infinity. We've seen an example of infinity minus infinity. And so you might be wondering what's going on with the infinity times 0 case. And so I was a little bit surprised when I was looking through the textbook to steal the examples. That's like there wasn't any examples in the text itself or like in the exercises where there is obviously an infinity times 0 case. And I realized, oh, there's a good reason for that. It's that anything that is infinity times 0, you could probably manipulate as 0 over 0 or infinity over infinity. So let me just put all of this here in big quotes when I do this equals, but if we had infinity times 0, we could rewrite that as an infinity times 1 over 0, which is infinity over infinity, or we could rewrite this as 0 times 1 over infinity, which is like a 0 over 0 form. So all of those equals need to be taken with huge grains of salt there. That's not equals in a true equal sense, but just means that they could be rewritten in a similar form. So if we have something like, let's go back to one of our most basic examples, the limit as x goes to 4 of x squared minus 16 over x minus 4. So we see that right now this is 0 over 0 form. We could have rewritten this as the limit as x goes to 4 of x squared minus 16 times 1 over x minus 4, where now this goes to 0 and that goes to infinity. Or if we had wanted to just make this really complicated, we could put the x squared minus 16 in a denominator and have 1 over x minus 4 over 1 over x squared minus 16. And now that goes to infinity, that goes to infinity. We have an infinity over infinity form. So in some sense, these first 3 you can kind of always change one to the other. So they're all interchangeable in some sense. So you might not run into any standalone infinity times 0 problems. And if you do, you probably could just rewrite it in a 0 over 0 or infinity over infinity form. In any case, you're going to be looking for some way to algebraically manipulate it. So that's the comment that I promised. To finish things off, I have one last example, and this is going to be one where we have symbols in our expression. And so what the thing that we want to do is we want to talk about the limit as h goes to 0 of h plus a, quantity squared, minus a squared, all of that over h. And so the comments to make here is that as h goes to 0, our numerator looks like a squared minus a squared, which is 0, and our denominator looks like 0. So we are in a 0 over 0 indeterminate form. So we should want to try to algebraically manipulate this down into something that we can evaluate by continuity. And so there's a reason that I'm stealing this straight from the textbook. There's a reason this problem is in here, which is when we start to do the derivative in chapter 3, we're going to have tons of problems that look like this. So the whole reason that we care about limits in chapter 2 is that we're just building up the machinery so that we can start talking about the derivatives that we want to talk about in chapter 3. So in some sense, this problem right here is the single most important example that we're going to look at in section 2.5, because we'll do something like this. We'll be doing this all the time when we start to do derivatives in chapter 3. Okay, so with that preface, let's go ahead and expand this out. So we want to algebraically manipulate it, so let's take a look at that numerator, see what goes on with it. So h plus a quantity squared is h squared plus 2ah plus a squared minus a squared, all that over h. Those a squares cancel. Of course, so limit as h goes to 0 of h squared plus 2ah, all of that over h. And so at this point, take a moment, see if you can simplify at all. So in the numerator, note that we can factor out a factor of an h. And so let's pull out that h. So h times h plus 2a, all of that over h. And so now we can cancel h from the numerator, h from the denominator. And we are left with the limit as h goes to 0 of h plus 2a, which we can evaluate now just by substitution. H is 0, 2a is a constant, and so our final answer is 2a here. And so, what you might not know this, but what we just did was that we just did all the calculations to evaluate the derivative of x squared. So we'll be revisiting this in Chapter 3.